So in this video, we'll start looking into the exponential smoothing approach and where it actually finds a difference from the moving average approach. So if you recall the moving average approach, we talked about multiple previous periods, okay? And so if it is a 4-period moving average approach, in essence, you have data from periods 1, 2, 3, and 4, and then based off of that, you choose the 5th period. That's your forecast, right? And essentially, you take the average of 1 through 4, which also tells you that when you make an average of 1 through 4, you are taking up those values and you are dividing by 4. In other words, you are giving equal weights to each of the previous periods. In this case, it's 25%, right? So you take 25% of the value at the first period, 25% the second, third, and fourth. And basically, when you add them up, that becomes your expected value or the average. The problem with that approach is that from a forecasting standpoint, as you move into the future values are expected to be more aligned to its next to kin values, which are the more recent values. As you move away from a future value, if you are trying to forecast for the 5th period, it might have a higher inclination or correlation with that of the 4th period. But compared to the first period, that correlation should not be too high, because then you are saying that there is almost constant. There is really nothing to forecast in that case. So that is a problem with the moving average approach, which is taken care of in the exponential smoothing approach, where it says that we will put more emphasis on the recent outcomes as opposed to the previous ones, as opposed to putting equal emphasis on all the previous outcomes. We'll put more emphasis on the recent outcomes. So that is one essence of moving from a moving average to exponential smoothing. The other essence is moving average requires a tremendous amount of data. If you're looking into a 12-period moving average, you need the previous 12 data points. Okay, if there are 100 such variables that you are considering, that's 1200 points. That's a lot of data. In the context of exponential smoothing, all you need is just the previous period. So it simplifies that process. So imagine that you are doing the new forecast for the future period, which is period T. Okay, and therefore the previous period would be period T minus 1, right? Because it's just the period before. So if I have to provide a mathematical spin to what I have written up here, if you look at the new forecast, let's suppose that forecast is being dubbed as F with a subset of T. Okay, that suffix of T basically means that you are forecasting for period T, which is equal to the previous forecast, which is the forecast for the previous time period, T minus 1, plus you have a smoothing constant that we are introducing here. Let's suppose we call that constant alpha, times previous demand minus previous forecast. Previous demand is your actual value. So I'm going to ask you this based off of what we have learned so far. What is in essence that term of demand minus forecast? And you got it right. It's called error, right? That's essentially what that idea is. So you are essentially looking at the error from the previous period, and you are making an adjustment to that error. So what happens here is a two-step process. First is you are not looking beyond. the previous period. So you are putting all of your analysis around the previous period and saying most of my analysis for the next period of forecast would be based off of my previous period. Two is the adjustment is made based off of that error. So in essence, if you have forecasted too high, guess what happens? That difference becomes negative, right? And so if you have forecasted too high in the previous period, this entire factor in the equation would lower the overall value, because that value would be negative. That will turn this positive sign into a negative sign, and it will lower the next period's forecast. So one more time, if in your previous period your forecasted value was very high, then of course your actual minus forecast would be a negative value. So that will then make that adjustment for the next period's forecast based off of that. In the same way, if your forecasted value was too low, then the actual minus forecast, or that error term, will be high, and it will increase and adjust the forecast in the next period. So that's where it plays the game when it comes to um, using the smoothing constant with the previous period's estimate of error. Okay, so that's how the exponential smoothing model is drawn. So what I'm going to do is I'm going to recreate this in the exponential smoothing data set. And again, this is intrinsic analysis. I am not looking into anything outside of just the sales numbers. Okay, sales numbers and weeks of data. That's all I'm looking at. Okay, so what we said is the forecast for period T would be the forecast from the previous period plus an exponential smoothing factor times the error from the previous period. That's essentially how we will capture these. So now let's start off with the forecast for week 2. So for forecast for week 2, where this will be, let me put this in the context, F2 is F1 plus alpha times error from 1. So when you are starting to design this model, you ask yourself, what is my forecast from week 1? I don't have forecast value from week 1. So in essence, I don't know what that value is, and therefore I have no clue as to what that error term is for the previous period. So I'm stuck. I can't use the exponential model. How do I provide a start? This is where the idea of naive modeling comes. So when you don't have any data, any previous data, the starting point of your analysis can oftentimes be naive. In other words, all I'm saying is to forecast for week 2, my starting point in essence would be the actual value from week 1. I'll start with that as my forecasted value. How about that? So that becomes my starting point of the analysis, because now as I look into the third period, when I'm trying to forecast the third period, now I can look into the forecasted value from the second period plus an alpha times the error from the second period. And now I have all of those data points here available to me. Well, almost all of those. So let's compute this in the same way we have drawn this equation. So when you look into the forecasted value for the third period, that's equal to the forecasted value from the second period, which is 669 plus you want to put in a smoothing constant here. I don't know what that value is. I'm going to put that, take that cell right now. I'm going to put in a value there eventually, times, and the error from the previous period is essentially your actual minus your forecast, right? And that gives you an output that Excel cannot determine because that cell has been given a question mark. So this is where I say that we start with a seed value. I don't know what that value for the smoothing constant is. Let's suppose that is 0.5, just as an example. And suddenly you find a corresponding value here because it took the previous forecast of 669 and it took the previous error of 706 minus 669 and used a smoothing constant of zero point 0.5 to smooth that and therefore create the forecast for the next period. So that's how this period's forecast has been created. And then I can drag all of these at this point now. And as you can see that all of these are giving you a different value. Can somebody tell me why? That's because it is taken E2 and there is nothing in E2. In other words, my smoothing constant is a fixed value here that I'm using for all of the other ones, right? And therefore, I need to fix that equation here. It's a simple fix. I look at my first equation and my E1 that I am using as my smoothing constant, I'm just going to go in there and hit the F4 button to make sure that I make that cell constant. I lock that cell because it's the same cell that I'm going to use for all of my other cells as well, especially when it comes to the smoothing constant. So now I have captured all of those forecasts. And so I'll do the same exact story in the context of forecast error, absolute percent error, and MAPE. You can do the sum of forecast errors, average error, and MAD and tracking signal yourself. First question is, because this is intrinsic analysis, and because I've already done intrinsic analysis with these four models, I want to still keep the parity and ensure that I give maximum chance to all of the models to have an apples and apples comparison. And therefore, in that context, I could have captured the forecast error all the way from the second week onwards, but in essence, to ensure that it's an apples and apples comparison, I shall again use the 6th week as my reference point so that I can capture the information and compare that with all the other moving average models at that point of time. So your forecast error again is essentially this value minus the forecasted value B8 minus C8. And so that becomes your forecast error and you drag that, it gives you all the other forecast errors. Absolute percent error. Absolute percent error again, you want to create the absolute value of the error and express that as a percent of your actual. Okay, so one more time, you want to capture the absolute value of your forecast error and express that as a percent of your actual value, right? And so ensure that the specific cell is given in percent. That way you can capture that percent and you drag that, and that gives you the overall absolute percent errors. And then when you come into MAPE or the mean absolute percent error, all you do is type in average and take the average of those absolute percent errors, close the parenthesis, hit enter, and that turns out to be 3.1%. Okay, that's your mean absolute 1% error. 3.1%. Now, if you are comparing with the other ones, 3.8, 2.8, 2.8, 2.9, you are naturally inclined to say the 3 period moving average is still the better one, right? Because you want your MAPE value to be lower, not higher. So this is clearly a high one. There is a small little problem here, and this is where we deep dive into the efforts and introduce a new concept in the context of analytic tools. The problem is all the calculations here, everything here is first rate. Everything is correct. The approach is correct, except for that value of alpha that you have chosen. Okay? The value of alpha that you have chosen is your choice. I woke up in the morning and I came up with a 0.5. What if I make that value 0.05? Oops, that number suddenly changes everything. Okay, what if I make that value 0.45? Then again that number changes. What if I make that value 0.5? Again that number changes. That's where we started. So the question therefore being, I know that my smoothing constant cannot be more than 1, so it has to lie between 0 and 1, but I just don't know what that exact value is. I'm just playing a trial and error, guesswork here, and I can't reach anywhere with that guesswork. Wouldn't it be cool if Excel as a software could help me identify that correct value of the smoothing constant for which my mean absolute percent error gives me a very minimum value? Because that's what I'm after, right? I want to minimize that MAPE, or the mean absolute percentage error. I want to minimize that, and in the process I want to figure out what is that smoothing constant that minimizes the mean absolute percent error. This is the basis of the need for optimization. When do you optimize? You optimize when you have multiple scenarios. So I could have put in a bazillion possible values between 0 and 1 on this cell, and each one of them will render a different value of the mean absolute percentage error. I want to choose one of those such that this output or this outcome is minimized. So what I'm going to offer to you is a very standard protocol of how an optimization problem is approached. And you can follow this protocol into any optimization setting. Okay, so let's go back to our PowerPoint, and I'll just go past these into a basic layout of an optimization problem. Okay, so an optimization problem is essentially having 3 parts to it. Okay, so the first part is what is your objective? That is always the first part, trying to figure out what your objective is. So in this story that we are currently pursuing, that objective is to minimize the MAPE, right? That's what we are after. We are trying to minimize the mean absolute percentage error. That's what we are after. Simple approach. In this context, it's about minimizing the mean absolute percentage error. You can have optimization applications in different situations. If you are a financial analyst, you're trying to minimize cost, you're trying to maximize profit, you're trying to maximize revenue. From an operations perspective, you're trying to minimize the time it takes to serve an individual, minimize the time it takes to get a product through a process. You want to maximize throughput or the number of people being served or the number of products that are being produced. So there are opportunities to minimize or maximize at multiple facets of a business. And that's where optimization works in multiple scenarios. In this specific scenario, because I am forecasting, knowing that I will choose the model that has the least error, I always have a chance to optimize, especially in this context, because I don't know what my decision variable is. Okay, so this is where I bring in the second piece of the puzzle when it comes to optimization, where I ask myself, what is my decision variable? In other words, in the context of this problem, I am trying to minimize MAPE by changing the smoothing constant, right? The smoothing constant is the one that I will allow the software to change accordingly so that it can get me the minimum value or the of the MAPE. The third piece of the puzzle comes primarily because of the nature of this algorithm. If I ask you to minimize or maximize something by changing a certain variable. So as an example, if I say y equals m times x, okay, and this is m, which I want to use as my decision variable. This is y that I want to maximize. If I don't tell you anything else, what would you use? You will use as much of a higher value of m as possible. Okay, so if m goes up, y will go up, and so I'll use a value of infinity for m, and then my y will be maximum. That's an easy fix. But that is how software works, which is why I am compelled to say this to in many of my classes, that at the end of the day, we are moving into a digital world. We are moving into Industry 4.0. Technology is looming large over us, but it is us who control technology. Or else all of these algorithms are what we define as greedy algorithms. They want to get into a result fast. And that's when we say, not so fast. Let's ask ourselves, can we put in any possible value for the decision variable? And that's where we ask ourselves, what are the constraints within which the decision variable value can be changed? In this case, the smoothing constant value can be changed within a set of what sort of constraints? And so in this example, as you can very well identify, the smoothing constant is a proportion that takes a value between 0 and 1, right? And so that is the constraint that you will use to try and change the smoothing constant value in order that you can minimize the MAPE. So in essence, you are optimizing that smoothing constant. The optimized value of the smoothing constant is the right value for which your MAPE is minimized. And we are doing that within a certain scope of changing that smoothing constant value. We are saying that you can do this only within the scope of the smoothing constant ranging from 0 through 1. This is a standard layout of any optimization problem. You get this concept clear, you can apply it to any setting, as we will see later on in the videos. What is my objective? What am I changing? or trying to optimize to reach that objective. That's my decision variable. And what are the constraints within which I'll ask my software to seek a solution? If there are no constraints, it will find a negative value of the smoothing constant to try and minimize the MAPE. So what are my constraints? Okay. So once I have these three things in place, it's very easy to set up the optimization table, as we'll see right now. So going back to the demand management template, all you need to do is under data, ribbon. If you recall, we did all of our statistical analysis using data analysis. There is also another add-in that I had asked you to download along with the data analysis add-in. It's called Solver. Okay, so you click on Solver and it opens up a background information that you have to upload into that solver input. And all I'm telling you here is there are only three sets of information that we are trying to gauge from here. First is setting the objective. What is your objective? You set a specific cell and you can set the objective to a specific value that you desire, or you want to minimize that specific outcome, or you want to maximize the specific outcome. That was the first step of the puzzle, as we discussed. Next is which value are you trying to optimize here? This is where you change the variable cells, right? And then you also add constraints in the process. And therefore, those are the three broad areas within which you would do your optimization. So let's go with the process here. What is our objective in this context? Our objective is to minimize the mean absolute percentage error or minimize the cell F21. And so I'll go to that set objective. I'll choose that cell. That's my F21 cell. I don't want to maximize it. I want to minimize it. So I choose the minimize option. By changing variable cells, this is the optimizing part of the process, right? By optimizing the smoothing constant, that's my decision variable. That's the second step of the puzzle. So when I click on that arrow, it allows me to choose a specific cell or a set of cells that I would want to change. And then last but not the least, subject to constraints. Do we have constraints? Absolutely. We want that smoothing constant to lie between 0 and 1. So I go to subject to constraints, I go to add, and it asks me for the cell reference. So cell reference, I'll choose that specific cell again, cell E1, less than equal to, I'll put a value of 1. Do I need to add one more constraint? Absolutely. I also want to use the other end of the spectrum, which is greater than equal to 0, right? So I want to do add, and this time I again choose the same cell, greater than equal to, and I type 0, and I hit OK. And then I make sure that the constraints have been properly loaded here. So again, three parts to the optimization process. What is my objective? What do I want to do with that objective? I want to minimize it by changing a certain variable. In this case, it's the smoothing constant. I want Excel, the software, the power of this software to optimize that value so that my overall MAPE is minimized. And oh, by the way, that smoothing constant can't take any possible value. I am constraining a certain set of values that should be used in the decision-making process. Hit solve. It solves and it asks me to keep the solver solution. We'll take a quick look at where the value has turned out to be. As you can see, I'm going to keep it. My smoothing constant is 0.086, and I can always clean this up by going to home and making it, let's say, 4 decimal places. My mean absolute percentage error suddenly got reduced to a 2.0%, which is actually better than all the previous moving average values that we were looking at. So that is the difference. All we have done is we have used the power of Excel in this case, and this can be done using any other optimizing software, to come up with a specific value of the smoothing constant that we would use in the exponential smoothing model, that would in turn minimize my mean absolute percentage error. You could have done the same exact thing with MAD. You could have calculated MAD and it would have done something very similar. You're also again trying to minimize MAD by changing the smoothing constant. So all you had to do was change the specific cellular reference for the objective function if you were using MAD. But in this case, we have used MAPE. So that is a very simple approach to how you can use optimization techniques, if you will. What we'll do in the next video is look into a few more approaches to optimization, primarily from a sourcing operation standpoint. You'll find that discussion quite interesting.